Okay, what if I told you that your data has a hidden shape, and that finding that shape could unlock patterns you never knew existed? Well, that's the whole idea behind a really powerful approach called topological data analysis, or TDA for short. It's a completely new way of looking at things, especially when you're dealing with super complex data sets. So today, let's dive in and see how it actually works.
All right, so to really get why TDA is such a game changer, we first got to understand the problem it was built to solve. We're living in this age of just data overload, right? And you think having more information is always a good thing, but honestly, it often creates just as many problems as it solves.
Yeah, there's this saying that just hits the nail on the head. More data often means more problems. I mean, look, this data explosion has given us some incredible stuff, right? Like image search, recommendation engines, the whole shebang. But, and this is a big but, anyone who's actually worked with data knows more data doesn't mean better data. Not at all. Real-world data, it's messy, it's noisy, it's just plain confusing a lot of the time.
And let's be super clear here. We're not just talking about big data. The problem of having a ton of it. TDA is designed for something even trickier: complex data. Now, what's that? Well, this is data that's not just huge, but it's also packed with noise and has a crazy number of dimensions. It's the kind of data where it's almost impossible to get a clear picture of what's really happening inside.
Okay, so this is where TDA comes in and offers a real breakthrough. It gives us a totally new way of seeing. It's like a framework for cutting through all that noise by zeroing in on one single fundamental thing: the data's underlying shape.
Really, at its core, TDA has this simple but really profound mantra. Data has a shape, and that shape matters. The whole goal is to take this messy cloud of data points and kind of boil it down to its essential geometric form. And that form? It's usually way more stable and way more revealing than the raw data ever was on its own.
I know, that might sound a little abstract, right? I mean, how can a bunch of disconnected dots even have a shape? It's a great question, and the answer, believe it or not, comes from a famous mathematical puzzle from centuries ago.
You're looking at the famous problem of the 7 bridges of Königsberg. The puzzle was simple. Could you walk through the city and cross every single bridge exactly once? People tried for years and nobody could do it. Then, this genius mathematician, Leonhard Euler, has a brilliant insight. He realized that all the details, like how big the islands were, how long the bridges were, that was all just noise. It didn't matter. So he stripped the map down to its most basic shape, a simple network of nodes and edges. And once he looked at that shape, the answer was suddenly crystal clear. Nope, it was impossible. And that right there, that's exactly the philosophy behind TDA.
So you can basically think of TDA as a modern tool that does for our messy data what Euler did for that map of Königsberg. It takes all this complex, high-dimensional data and translates it into its fundamental underlying shape. And this simplified shape is way more robust to noise, which helps us spot patterns that would otherwise be completely invisible.
And the process for doing this usually follows a pretty clear pipeline. It's basically 4 steps. You start with your raw data. Then you translate that data into some kind of shape, like a network or a graph. Step 3, from that shape, you pull out the key topological features. We're talking things like connected components, loops, holes, that sort of thing. And finally, you take those features and feed them into your analysis to power, well, everything from simple stats to really advanced machine learning.
Okay, so the main engine that drives this whole process, the real workhorse, is a technique called persistent homology. Now, the best way to think about it is like a special lens for looking at your data. As you kind of zoom in and out, changing the scale, this lens keeps track of all the shapes that pop up. Clusters, loops, voids. But here's the magic trick. It's all about persistence. The shapes that stick around across a lot of different zoom levels, those are your real signals. The ones that just flicker in and out for a second, that's just noise. And the algorithm learns to tell the difference. But here's the thing. While persistent homology is the famous one, the workhorse everyone talks about, it's really just the tip of the iceberg. The whole field of TDA is this massive, constantly evolving universe of super specialized tools, and each one is designed for different kinds of data and for answering different kinds of questions.
And when I say a universe, I mean it. Just look at this list. We're talking about persistent topological Laplacians, persistent Dirac operators, sheaf theory, multiscale Gauss link integrals. I mean, it's just a wall of crazy-sounding terminology, right? Don't worry, I'm definitely not going to try and explain all of these right now.
The reason I'm showing you this isn't to scare you off with jargon. The whole point is to show you that all of this incredible mathematical complexity, it exists for a reason. And that reason is to solve incredibly complex real-world problems. And the impact?
It's honestly staggering. These advanced methods are out there right now discovering new subtypes of cancer. They were used to forecast the dominant variants of SARS-CoV-2 months ahead of time. People are using them to define totally new player roles in basketball analytics and to predict how well a drug will bind to a protein. This is where that abstract idea of shape stops being abstract and becomes a real-world superpower. But of course, a field this exciting isn't just standing still. You know, like any really active area of science, researchers are constantly pushing the boundaries. And what happens when you push boundaries? Well, you discover new challenges, right there at the frontier of what's even possible.
So this brings up a really natural question, doesn't it? Are there limits to how powerful TDA is? I mean, can it handle just any kind of complex data we can throw at it? Well, as it turns out, researchers are finding that, under very, very specific conditions, the answer is actually no.
They've actually given it a name, the curse of dimensionality on persistence diagrams. So here's the problem. In some really specific situations, think extremely high dimensions but only a tiny number of data points, the noise itself, the high-dimensional noise, can actually start to form fake phantom shapes. And these false shapes can totally trick the TDA algorithms and make them less reliable. It's this weird case where the noise is so intense it actually starts to look like a real signal.
And you know what? This illustrates something so brilliant about how science works. Finding this curse isn't a failure of TDA. No way. It's actually the opposite. It's the sign of a healthy, self-critical, mature field that is actively figuring out its own limits, so it can then figure out how to smash right through them. That is exactly how progress is made.
So, when you boil it all down, topological data analysis gives us this incredibly powerful new lens to see the world. It's a method for tuning out all the static, all the noise, and finding the fundamental structures hiding inside our most complicated data sets. Which really just leaves us with one final and I think really exciting question. What other hidden shapes, in medicine, in science, in our own society, are just out there, waiting for us to discover them?